Now, I've been here 6 months, so my inaugural lecture is about the World Trade Center 7, and I know there's a number of people in the audience that want to ask a number of questions. Can you hold on to those till the end, please? And there will be a Q&A session. So, why did I choose the World Trade Center 7? Those that know me, I left school at 16, I was an apprentice, I was a draftsman, I've been a structural engineer all my life. I started off, as I say, as an apprentice, 5 years working with different companies, then I went to university, then I carried out a PhD looking at structures in fire, then I worked for the Steel Construction Institute, then I worked for the Building Research Establishment, then I moved as a Professor of Structural Engineering to the University of Manchester, and then I was lucky enough to come back to London, where I was born, to lead Queen Mary University of London. And during my career, I've done a lot of research on fire and fire in buildings. So why have I chosen the World Center 7? Well, if you look on the internet, you will see a number of documents. I was an expert witness on the World Trade Center 7 from 2007 to 2011. I have done a number of projects as an expert witness. And of course, as an expert witness, and I can discuss about that for the whole hour, but as an expert witness, your duty is to the court. Of course, you are paid by the client, but your duty as an expert witness is always to the court. And there has been some cases where I've given my opinion to the client and they paid me straight away and shoot me out the door.
I've had that.
Because my duty is to the court and your integrity is everything. So now this is my explanation of why the World Trade Center 7 collapsed. And I'm going to take you through it. I apologise, I have a number of slides. So please hold on to your seat because we're going to move very quickly. So, going back to that awful day, there you can see the World Trade Center towers, World Trade Center 1, the North Tower, and the World Trade Center 2, the South Tower, and the building I'm going to talk about is the World Trade Center 7, which is the 47-story office building. No one was killed in that building, but of course on that day a number of people were killed in the towers and the surrounding areas. Again, you can see the actual where the towers are. So you've got World Trade Center 2, 1, the North Tower, and the building we're going to talk about is World Trade Center 7. The only building that is known to have collapsed due to a fire. Again, this shows the building. This is the World Trade Center 7, the 47-story office building. As we go through the presentation, I would ask you to keep an eye on the penthouse here. And you'll see this as we go through the presentation. So there again is another picture. This is the top of the building. You'll see here, this is the North Tower. So what you're looking at is the North Tower is down here. This is the World Trade Center. In this view, you're looking towards this elevation. And you can see the east penthouse here, which is the east penthouse at the top there. So of course, September 11th, 2001. Those that are old enough can remember that awful day. Just short of 3,000 people died. And more than 6,000 people were wounded as the planes were deliberately crashed into the two towers. The South Tower, which is the furthest one away from the World Trade Center 7, collapsed at 9:49. And this is classic progressive collapse, where the building all comes down in one go. And we'll talk about progressive collapse as we go through the presentation. The North Tower collapses at 10:28 a.m. And again, you can see the North Tower here, how dreadful it must have been for people that were stuck on the top there, seeing the South Tower come down. And then you can see the North Tower coming down as classic progressive collapse. Damage to the World Trade Center 7. I should have said through the time as an expert witness, I went through thousands of documents, photographs, looking at what happened during that day, together with other expert witnesses that were involved. And you can see, as the North Tower is coming down, the debris that is falling onto World Trade Center 7. Not many pictures were available on the damage of the World Trade Center 7, but you can see here, so the North Tower, which was here, as it came down, it gouged through the World Trade Center 7. That was the structural damage that you see there. That can be seen over 23 floors. It then obviously caused a fire, and then there was a fire for 7 hours. And it was a classic travelling fire. We will look at that closely, where the fire started to travel throughout the World Trade Center 7. And then if you can see the plan of the World Trade Center 7, this was the North Tower, World Trade Center 1. This was the extent that we could find on the damage that was caused, and there was damage on the southwest corner. That would not cause collapse. That was superficial damage, but it did obviously start the fire. As we go through the day, as I said, we looked at a number of photos. These are lines that we put on, and we followed the fire through the building for the 7 hours to see what was heated and what was happening as you go through those 7 hours. And then, debris from the collapse of World Trade Center 1 at 10:28 ignited fires within World Trade Center 7. So it was standard office fires, there was no jet fuel, it was only superficial damage, superficial structural damage, started the office fires, the fires started to travel through World Trade Center 7 for 7 hours, and then collapse occurred at 5:20 p.m. Only known case of a high-storey building collapse due to fire. So, to explain what happened, we need to consider two things. We need to consider progressive collapse. I talked about it earlier, and we're going into detail now what is progressive collapse. So we need to discuss progressive collapse, or you might hear people talk about disproportionate collapse. What it means is if a part of the building is damaged, it causes the rest of the building to fall down. And that's progressive collapse or disproportionate collapse. And we need to discuss fire resistance. So I'm going to start with progressive collapse, go back to the World Trade Center 7, put that into context, and I'm going to come out, talk about fire resistance, all the background about fire resistance, and then I'm going to go back into the World Trade Center 7. Can you hear me at the back? Yep, good. If you can't, just shout. So, let's go to progressive collapse. Now I'm going to go right back in the UK to Roland Point, which was in 1968. So Roland Point, again, those of you that remember, it was a turning point of the way we design buildings within the UK. So Roland Point, what actually occurred was that there was a gas explosion on the 8th floor. There was a gas leak. Someone up there then decided to make a cup of tea, turned on the oven at the time, and there was an explosion. So, on Roland Point, the way it was built, you had a wall, you had a floor, wall, floor. There was no time between the floor and the wall. So when there was an explosion, what happened is the floor went up, the wall went out, and then the floor fell down because it was not tight. So when the floor then fell on the floor below, it was like a pancake effect. Bang, 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 all the way down. There was no time, there was no redundancy in the system. So when there was an explosion and the floor and the wall came apart, and the floor then came down because the wall was blown out, it hit the floor below, and it came down as progressive collapse. And you can see progressive collapse that occurred in the corner. There was an explosion here, the wall came out, this floor came down, bang, 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 all the way down. Looked at that, of course we can't accept that, that is progressive collapse. That is progressive collapse or disproportionate collapse. And again, there was 4 people that died in Roland Point. So, looked at the building regulations. And it was this that was a turning point in the building regulations in the UK. So the changes to the building regulations, it was designed, the changes were put in place to make sure that progressive collapse does not occur. How do they do it? You introduce continuity at the connections, or you provide alternative load paths. Basically, what you're trying to do is put redundancy in the system, so that if there is a failure of a part of the building, the rest will not fall down. So a failure of a part of a building will not result in overall collapse. So in 1976, the building regulations, those of you who are old enough, this was called the Fifth Amendment. It said the building shall be constructed so that in the event of an accident, the building will not suffer collapse to an extent disproportionate to the cause. That's why it was classed as disproportionate collapse, progressive collapse. i.e. if one member in your building fails, the rest of the building does not fail. It was limited to buildings with 5 or more stories. This resulted in what we class as robustness or redundancies in the system. So if we go to the building regulations now and the approved documents, now the building regulations basically say that the building should be constructed so that in the event of an accident, the building will not suffer collapse, etc., etc. If you go to the approved documents, if you follow those, you actually make sure you comply with that building regulation. You've got 3 ways that you can do it. One is tying, where you provide horizontal and vertical ties. Another one is bridging. So if you lose an element, or lose a column or part of a building, you will bridge across with the rest of the structure. Or you design a key element. And a key element, you design an untied member to resist 34 kilonewtons per metre squared. The engineers in here will know that that is a massive load. I've only done it once on one building, and it costs a fortune. So let's take those in turn very quickly. Tying, design methods. So this is a floor. Typically, it might be a composite slab where you put concrete. This is a metal deck. This is a steel beam. This is a steel column. And the idea is that you look to see whether you can tie these together so that if there is any damage, they're all actually tied together. Remember, go back to Roman Point. The walls and the floors were not tied together. So when there was a disturbance, an explosion, they came apart, and then the rest just fell down because they weren't tied. This gives you an example of how it's worked. This was a building in London that was subject to a terrorist bomb in '92. And you can see the tying effect of the beams, that the structure has remained in place. This is a picture of my old boss at BRE. But you can see that this structure has actually performed very well. Round the corner here is a building I designed, and that shows a bit of my age as well, and I designed it with a key element. I'll come back to that in a minute. The other area is bridging. So again, if you look at the approved documents, you take an area where you've got some damage and you look to see how you can bridge the rest of the structure over. And again, this was an explosion in London, and you can see where we've got 3 ground floor to first floor columns removed by explosion, but we've got bridging over. This is just scaffold after, but we've got bridging over, which allowed the structure to be remain in place. On key elements, you can design an element anywhere for a pressure of 34 kilonewtons per metre squared. Where this has come from is based on a flank wall gas explosion on Roman Point. Someone came up with that figure and it stuck as a key element. Put that into context, the floor we're standing on, or an office floor, is typically designed for 2.5 plus 1 kilonewtons per metre squared. So you can see that if you're designing for that, you actually need quite a big structure. And it's used to determine a notional load applied to the key elements. It's not, when you look at it, actually related to a gas explosion, even though if you go back in history, that's where they say it's come from. So, that's the rules in the UK followed in Roman Point. So, let's go back to the US. So, progressive and structural collapse. The building codes lack explicit structural integrity provisions to mitigate progressive collapse. So in the US, they didn't have any of these rules. So it was not designed for progressive collapse. They say that federal agencies have developed guidelines to mitigate progressive collapse and routinely incorporate such requirements in construction of new federal buildings, not the case of World Trade Center 7. The UK incorporates these within our practice. I've already shown those. New York City adopted by rule in 1973 a requirement, remember this is where the World Trade Center is, for the buildings to resist progressive collapse under extreme local loads. That sounds good. The rules which were adopted after the World Trade Center towers were built, but built before World Trade Center 7 was built, apply specifically to buildings that use precast concrete wall panels, i.e. not World Trade Center 7. So World Trade Center 7 was not designed for progressive collapse. What does that mean? Let's go back to how World Trade Center 7 was built. Here you've got the steel structure, and the structure was built over a power substation, which meant that we need structures that would transform loads across the structure. And the area of interest is if you look between the 5th and the 7th floor, we had a number of cantilever trusses and a number of very big trusses. Why do we have the trusses? You can just see the columns coming down here, but of course then the load being transferred not to a column that's directly under, because there was no room to put that. Remember, there's a power station underneath, but a column that was going either side. There was 3 big trusses, truss 1, truss 2, truss 3, and all these cantilever trusses, which were distributing load across the structure. They were not designed for progressive collapse. So if any of those are hit at all, we're in serious trouble. There's no redundancy in the system, there's no tying in the system, there's no bridging in the system. So if anything hits that structure, we are in trouble. And you can see that in a bit more detail. You've got column 79, I'll come back to that one in a minute. Column 80, where this truss is, column 77. So these are big trusses, transferred trusses here, and then cantilever, and these are trusses going out there. No redundancy in the system. So if anything starts to hit those, we are in trouble. And if anything starts to hit those, we then start to have horizontal progressive collapse, and we'll look at that in a bit more detail as we go through. So, going back to the pictures, we can see the World Trade Center 7 there. East penthouse, keep an eye on the east penthouse, you can see it at the top. Where is it? East penthouse, you can see it there.
At the top.
Yeah. Where is it? It's gone. It's gone there, and you can just see daylight coming through there. And obviously totally gone, so you can see. So that gives us a clue, first of all, where is the initiating event. And there you can see a picture of the building just starting to fail. You can see the kink in the actual northeast corner, you can see the kink of the penthouse. So this is the penthouse. This gives us a clue. The initiating event is here, 79 to column 80. So you can see this is the area that actually we're interested in. This is a big girder, steel beam. Those are not structural engineers. Looks like steel beam, but very deep. So that's why we call them a girder. This is spanning 45 foot. In UK money, 13.7 metres, or EU, I should say, and 52 foot going in this direction. This is an interesting actual layout. You can see the beams going perpendicular to this girder and then going in the other direction, the other side. Very important when we come to looking at this in fire. At the moment we're looking at progressive collapse and initiating events. So, we've got 79, Anything that happens around here and starts to collapse in this area and then starts to hit this, we've got problems. Because these have got no redundancy whatsoever. If this starts to collapse, this will just go bang, 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 horizontally right across the building, and then the whole thing comes down. Okay, so that's progressive collapse. So just remember when we're there, we're looking at this area, initiating event. As soon as something fails here, there's no redundancy. In the UK, we would never design them like this. We would put a lot of redundancy in these trusses. Once it starts to locally fail here, hits these structures, it's horizontal progressive collapse right across those trusses. Once you've got there, the whole building then just comes down. And what you're actually seeing is the outside of the building coming down. The inside's already gone in this area and then across there. Okay, so progressive collapse. Hold on to that. So that shows where the initiating event happened and then what actually happened afterwards as you went through the progressive collapse. We now need to go back and look at fire resistance because we need to look at the initiating event. So remember, this was 7 hours after. So I'm quickly going to take you through fire resistance. And I'm going to go back, I'm sorry, to basics because then I can put that back into context into the World Trade Center 7. So, fire engineering or structural fire engineering, why do we design structures for fire? And this is where I spent a lot of my research work. We could go right back to the Great Fire of London in 1666, and then the first legislation was really the Building Act 1667. Houses were to be built in brick and stone instead of wood, and the number of stories and width of walls were carefully specified so that you had space between the buildings and you're looking for the spread of fire. And streets, as I say, wide enough to act as a fire break. Go through history and there has been a number of fires, and of course there's been a number of fires recently as well in London, but you can look at fires all over the world. This was the Windsor Tower in Spain. It got the US. This was actually Paddington in London. This was, Paddington in London. That's Broadgate, and that's one in Brazil. So, structural fire engineering, this is my definition, is the science and art. Engineering is all about art as well as science. It's the science and art of designing and constructing with economy and elegance buildings, frameworks and other similar structures to protect people, property and the environment from the destructive effects of fire. So, fire safety in buildings, the aims, to limit to acceptable levels. Remember this, acceptable levels. Probability of death and injury to people, property loss and damage to the environment. People, we're talking about occupants, firefighters, public in the proximity of the building. Property loss, there's a lot of issues about loss of business, so when there's fires in buildings, it actually leads to whoever owns that building actually a loss of business and going out of business in some cases. And damage to the environment, where here we're looking at emissions of gaseous pollutants and runoff of water we might use to fight a fire. Minimum levels of safety, which is life safety, is covered by legislation, not property loss, life safety. And they're given in the building regulations, and there's been lots of talk about building regulations recently, and it seeks to ensure reasonable levels of health and safety for people in and around buildings. The regulations relating to fire cover, means of escape, internal fire spread, linings and structure, and that's what we're going to look at because that's the structure part of it, external fire spread, access and facilities for the fire surface. And it only covers life safety because that's the minimum levels of legislation. So if you look at the British building regulations, you'll see it as B3, and we've got internal fire spread, linings and structures, and it says, this is the regulations, this is what you've got to achieve. The building shall be designed and constructed so that, in the event of a fire, its stability will be maintained for a reasonable period. That's the building regulations. Now, there's a number of ways that you can make sure that you comply with the building regulations, and the obvious way in the UK is to use approved documents, and that's approved document B. People get confused because the approved document B is about this big, and they think that that's building regulations. It's not. That is a building regulations, just that statement. So, you can address the building regulations, as I say, a number of ways. One is through the approved document B, which is classed as a prescriptive approach, which basically says, you shall construct this building this way. And that will give you things classed as fire resistance, travel distances for escape, the size of your compartmentation, etc., etc. But you can approach it a different way, which is a performance-based approach, which means that you can look at the way the structure really behaves under a real fire and how the actual structure itself will perform. And that's why it's called a performance-based approach. And you can, with the building regulations, actually go between the two, but you're going to have to take a lot of care. And you'll see that with the review of the building regulations at the moment, where people will perhaps jump between the two without really understanding what they're doing. But as I say, a prescriptive approach states how the building is to be constructed, which is typically the approved document B, which we'll come to, and a performance approach states how the building is to perform under a stated criteria. So, prescriptive approach, set rules. Some engineers like this because I just follow rules, but actually proper engineers shouldn't be doing this. They should understand exactly how things behave under any event. So, but let's look at prescriptive approach, set of rules. For example, minimum fire resistance for members. This is looking at structures, and I'll come to that in a minute. You have a minimum fire resistance, minimum fire compartment size, minimum travel distances. So if there's a fire in here, we've got travel distance to getting out of the building. All these are specified. Minimum number of exits, etc. So what I'm going to talk about is the structural side of it. So the structural side of it looks at minimum fire resistance for members. That's structural members. So if we go to the approved document B, first of all, it states a fire-resistant period time. And this is based on the height of a building and the occupancy of a building. So if you took offices, you actually, for an office under 18 metres, you must have 60 minutes fire resistance. What does that mean? I've seen senior engineers stand up and say, that means the building will survive 60 minutes in a fire. No, it doesn't. And I saw senior engineers stand up after the World Trade Center and say, these had 2 hours, we're talking about the towers, 2 hours fire resistance, they should have lasted 2 hours. No, it doesn't mean that. It's a total misunderstanding. What it actually means is that the elements of your structure will last 60 minutes in a standard fire test. It means nothing else. So what is a standard fire test? It's a furnace and it follows a standard temperature time curve, and that's it. You can see it there. So for 60 minutes we will reach a temperature within the furnace of 945 degrees. And we will look for a structure load-bearing capacity, making sure that the load, so if you put a beam or a floor within a furnace, you put a load on it, make sure that it resists the load for the duration of the test. As soon as you hit 60 minutes, you take the load off because it's hydraulic load. Pass the test. Insulation. It means if it's a floor or a wall, the side that's not exposed to the fire must not increase its temperature by a maximum of 180 degrees or an average of 140 degrees over the area. And integrity means that flame can't come through the walls or the floors. That's the criteria. They're the standard fire tests. For a column, 3 metres. For a wall, 3 metres. For a beam, 4.5 metres. And for a floor, 4 metres. And the floor looks a bit bigger than that in here. But that's a standard fire test. That's what you're testing. History of the standard fire test, you can go back to the 1890s. On the behest of the insurance companies, they wanted to look at how structures or how parts of structures actually behaved. So it's the early attempts at establishing structural fire behaviour were made at the behest of the insurance companies. 1917 was the first US standard. 1932, the BS standard, and then you can see the US ISO come in and then the Eurocodes. 127 years of testing and still going. What does that mean? It means actually we're ignoring what happens in real life, and all we're concentrating on is what happens in the standard fire test. And then people start to play games. Because if I need a fire certificate for a fire door that requires 60 minutes fire resistance, I want to design that door so it achieves 60 minutes fire resistance. I don't want to design that door a bit thicker that it achieves 62 minutes or 63 minutes, because I'm not competitive. And of course, I only need one fire certificate, so I can test this 6 or 7 times and just get over it. I've seen tests where I've designed large-scale tests and I've had a 60 minutes protection on the walls, the plasterboard, and I've designed it so that I follow the standard fire curve, and at 60 minutes we can just watch it peeling off. It's done what it said on the tin. But actually the fire was carrying on and no one's putting the fire out. So you play games, and that's what's been happening. So you play games to just pass the fire test. So of course in the fire test, you carry these out in the lab. It's nice, got a nice lab coat on, it's nice and dry. This is a steel beam that's got an intermescent paint on. An intermescent paint is nice because it looks like a paint, but when you start to heat it, it chars. And when it chars, it will insulate the steel, because steel loses strength and stiffness when it gets hot. This is nice. This is in a lab. This is going to go into a furnace. Testing the thickness, make sure it's absolutely perfect. This is an intermescent inside. It's not cured properly. The damage of test, reality. So you can see what's happening. We're just focusing on what's happening in a standard fire test. And of course the limitations of the standard fire test. So that's the standard fire curve, you can see there. In reality, a fire doesn't follow that. A fire will ignite, you get a bit of smouldering, you get a bit of flashover. So a fire might start in the corner, as soon as it hits the scene, and it goes straight over in seconds, and everything in here will catch fire, and that's called a flashover. You get the flashover, and it will start to heat up. You'll get to a point, and then it will start to cool down. Standard fire test just follows that curve to the point you finish the test, turn the test off, take the load off, you passed or you failed that test at that time. So, it's not a real fire on the standard fire test. I shows that standard fire test for a beam is 4.5 metres. We don't use 4.5 metre beams in buildings. You know, we're up to 15 metres plus. So this is what we're testing, this is what we're building. And of course, limitations on the prescriptive approach. So members within buildings. This is columns, this is floors, this is walls. I was lucky enough to work for the Building Research Establishment and the Steel Construction Institute before that. And we actually built a number of full-scale buildings. You can see a person just standing there, and then we set fire to them. Cool, did I have some fun? I don't know, is Tom and David here? Ah, David, my old boss. We had some fun, didn't we, David? And we set fire to these buildings and another building. But members within buildings. So you can see a column, standard fire test. Does this column behave exactly the same in a building? No. Floor, does this floor behave as it did in a standard fire test? No. And the same with a wall. So the limitations, the assumption that we take if we follow the prescriptive-based approaches, the members will provide the same level of performance, i.e. behave in the same way when they form a part of the building, which is incorrect. We know that as engineers. So, as I said, and it's great to see David here, built 2 buildings. This was a 8-storey steel frame building. There was a number of compartment fire tests. We were looking to see how the building behaved, and we were looking to see how the building behaved with unprotected steel. So steel does lose strength and stiffness. Typically for a fully loaded steel beam or steel column, if it's heated all the way around, you protect it to make sure it doesn't get above 550 degrees. Or for a beam, if it's got a floor on the top, you protect it so it doesn't get above 620 degrees. That's a rule of thumb. I'll come back to that in a minute. So we were seeing how it would behave with no protection on the steel. And this is a concrete frame building, and we set fire right down the bottom here, mainly because we didn't want to keep on walking up and down the building, so we decided to set fire at the worst place, which was a compartment on the floor. So, the steel frame building, which I must admit was a great time working for BRE, maximum steel temperature went up to 1150 degrees. And all this data is on the website. All this data you will find on the one-stop shop that I set up in Manchester. BRE was kind enough to allow that data to be published, and you'll find it. We haven't updated that website for a number of years. That was paid for by government at the time. I've left Manchester, but it's still on the website. On the concrete one, we got up to a maximum atmospheric temperature of 950 degrees. So then, going back to detrimental behaviour, you can see on, I'm going to fall off now. You can see what happens in a furnace with a wall, but actually in a real building, you've got the movement of structure around the wall as well. So you've got loads that are coming onto the wall, which are not taken into account in the standard fire test. And you can see that here, where you get a fire within a compartment, deflection of this floor above, deflection towards the fire of the wall, and then different loads going onto the wall, which is detrimental to the stability of that wall, which you're not looking at in the standard fire test. And you can see some examples there. These are compartment walls. We've got the steel frame. This is where the fire was. This is starting to deflect. Obviously, you can see the damage to the compartment wall, but as this has come down, this has put additional load on that wall to cause it distress. And you can see here, there's a fire behind this wall, and you can see the damage to this wall, and you can just see some precast concrete planks on there as they move and put different load. You're not considering that in the standard fire test. Other detrimental behaviour, this is the concrete building, and you can just about see a deflection here. This is where the fire was, and the movement of this, and then putting additional loads on that column. This carried on moving as that fire started to cool. We had all the equipment all set up, and we could see the movement of this structure, and we're very concerned about it. Remember, this is on the ground floor. In the meantime, the fire brigade that were there just in case anything happened were all lined up here taking a photograph, because they thought the fire was out. And we had to try to pull them away to say, no, you're actually more danger at the moment than you were at the height of the fire. And you can see, obviously, the displacement and the distress to the bracing there as you've got movement of the wall that side. Again, detrimental behaviour. You're not picking this up in any of the standard fire tests. And you can see the movement there. So, if we were looking at the building as a whole, we would need to ensure the building can resist or accommodate horizontal displacements. Other limitations. I've already mentioned that this is the standard fire curve in the standard fire test. This is the real fire, and you go through the cooling stage. You do not, in a standard fire test, consider the cooling stage of a fire, which actually is where a lot of damage is done. So if you start to heat up a steel beam, the engineers here, the steel will obviously lose strength and stiffness. It will become plastic as it pushes against the connections. then it will cool down and try and contract from a plastic, a permanently deformed state. So therefore, it will have a lot of tension onto the connections, and it will start then ripping the connections. And you can see here, this beam isn't in Carlington. This is another fire I went to. This beam's on the floor. It's fallen down. Here you can see bolts that have been sheared, and here you can just see that the connection here has failed, and actually it's ripped down the side of the connection during the cooling stage of the fire, which is not considered in a standard fire test based on fire resistance and those prescriptive approaches. Other detrimental behaviour, you can see in the floor the actual damage there. You can see the column here. This is due to restraint of the structure above, not considered in the standard fire test. You can see all the damage around here, and again damage to the column here. So detrimental behaviour. Going to the actual concrete building, you can actually see spalling here where you've got exposure of the reinforcements. So in concrete, of course, concrete's good in fire, it's a good insulator, but the steel rods or the steel reinforcement you use for tensile strength in concrete, you don't want those exposed. If you have spalling, i.e. the concrete starts to come off and you expose that reinforcement, you're in a bit of trouble. Because of high compressive forces, i.e. the restraint of the rest of the building, that induced more spalling. So therefore the concrete cover fell off and exposed the steel frame. That is detrimental, you won't pick that up in a standard fire test. But that's all the detrimental stuff. There's also, when you consider real building behaviour, there's beneficial behaviour as well. So when you look at beneficial behaviour, go back to the steel frame buildings, you have what is classed as tensile membrane action. So you will not pick this up in a standard fire test, where basically you're looking to see how the structure can perform in a sort of catenary action. And this is what we class as tensile membrane action. And I've done a lot of work looking at this, and a number of design methods are used in the UK to allow you to take into account that beneficial behaviour. I talked about high compressive forces. High compressive forces can cause spalling, but it also then creates compressive membrane action. Now, compressive membrane action is when you start to force against the restraint and actually start to lock in. And then, of course, that will give you beneficial behaviour. So, going to the prescriptive approach, I've just taken you very quickly through looking at detrimental behaviour, beneficial behaviour. So, the prescriptive-based approach, based on a standard fire test, the advantages. As an engineer, it's actually quite easy to design something because you just use simple rules. You use simple rules, cover on reinforcement, protection to steel beams, and you use those simple rules. Experience has shown that the approach works. Well, I've just shown you loads of detrimental behaviour, beneficial behaviour, but to date, actually, we don't have buildings falling down around the world. Come back to the World Trade Center, but we don't. So actually it looks like it might work. An approach is easily understood by all parties because that's the approved document. Follow the approved document, follow fire resistance, everyone understands it. Fine. Disadvantages. Actual structural behaviour is ignored. So you're ignoring how it behaves in a real building. You're ignoring how fires really behave. So the effect of real fires is ignored. Level of safety and robustness are unknown. So if someone asks me if you follow a prescriptive-based approach on fire resistance, how safe is this building? No idea. Because all I've done is just follow a prescriptive-based approach. Optimum solution in terms of life safety, economical impact and environmental damage is unknown. So, on the prescriptive-based approach, actual structural behaviour is totally ignored. The effect of real fires is totally ignored. So as an engineer, what are you doing? But buildings haven't fallen down. Is there compensating errors? because I've talked about detrimental behaviour, I've talked about beneficial behaviour. Do they compensate for each other? Yes, possibly. But I'll tell you what, keep those costs. But there is another way. You can go down a performance-based approach. And as engineers, you can start to look at the fire behaviour, real fire behaviour. You can start to look at the thermal response, i.e. how the structure heats up. And you can start to look at the structural response. So on the fire behaviour, you could still keep the standard fire curves if you want, but start to look at loads and how things heat up. But you can then look at time equivalence, how real fires behave compared to your standard fire. Parametric curves, how real fires, SO models, CFD, travelling fires. You can look as an engineer, you've got all the skills to do that. Thermal response, you can look at test data, but you can look at simple heat transfer models, or you can look at advanced heat transfer models. And structural response, even looking at members, you can look at the proper load on the member. Better way of doing it is looking at a frame or a part of a structure, or even better as a whole building behaviour in a fire. That's a performance-based approach. So you start to look at real fires, the heat transfer, and the structural response. So the advantages, it allows actual behaviour and robustness of the building to be assessed. So if a client then asks me, how safe is my building? What robustness have I got in my building? I can start to answer. It allows the optimum design to be determined, taking into account life safety, financial impact and environmental issues. So you've got the life safety, which is covered by your legislation, but actually you might want to start to put more robustness, more capability within your structure to resist the fire that might occur, and can be used as part of an assessment for multiple risks, i.e. if there's an explosion followed by a fire. Disadvantages, well of course it's much more complicated. So you're not following a standard table, standard rules, you're actually looking how the structure will behave, and the client may not want to pay for that. You usually find when you say, well, okay, I can do you a proper design. No, just what I need to get through building regulations. Requires multidisciplinary skills. Design can be complicated, which also means the design is complicated that you put forward, which also needs to be checked as well by someone else. And change in building use may make the fire design invalid. So if you design it for a fire and you change the fire load or the use of the building, that will change that type of fire that might occur. But the performance-based approach has been used in a number of buildings in the UK. I've been involved in the Shards, WSP did the design, one of the remarks here, so WSP did the design, but Suffolk asked me to carry out the third-party review on that one. Linedin Hall, which is the cheese grater, Arab did the design. Again, I did the third-party review. Heron Tower, Arab, and I did the third-party review. Pinnacle hasn't been built. But those buildings are based on a performance-based approach. And it's based on a performance-based approach to get obviously the optimum design, but the safest design. And actually, there is more fire protection placed on columns in those buildings compared to the prescriptive-based approach. Okay. So, structural fire engineering, prescriptive approach, head in the sand, because as an engineer you don't know how this is going to perform. Keep your fingers crossed, performance-based approach, greater understanding of how buildings behave in fire, more robust designs, and more economic designs, because you design them properly to withstand fire. Right, that was a quick run-through on fire engineering. Let's go back to the World Trade Center site. So, 47-storey office building again, just to remind yourself, we've already done progressive collapse. We are now looking for the initiating event. So, going back, we got, as you saw before, the penthouse. We can see the kink here. The inside of the building here has collapsed, hit that transverse structure, progressive collapse along there, and then that whole thing has come down. We're around this area, as I said before, column 79. We're looking at the girder here, 45 foot, and the beams here 42 foot. Carried out modelling. The modelling was carried out by Arabs, and we looked at the structure around this area in a lot of detail and with different fire curves and fire analysis. Going back to how this was designed, it was designed using the prescriptive-based approach. And the prescriptive-based approach was looking at how the parts of the structure perform in the standard fire test. And the standard fire test in North America is slightly different, and I'll come back to that in a minute. And based on the standard fire test, fire protection was placed on the steel beams, steel columns, and the underside of the steel deck. So in North America, there is a slight difference to the standard fire test. The sizes are the same, but what they actually look at is that they allow the structure to be restrained or unrestrained. So around a floor or a beam, you can have a fire test where they restrain the actual beam and column. What does that mean? Because when something heats up, it will expand, and if it starts to push against the restraints, forces starts to be induced within the actual structural member. It's beneficial in the instance where you can get what we class as compressive forces, which will come into a beam or a column, which will allow it to withstand more load. That's the difference in North America. So fire protection was specified as 2 hours for beams and floors and 3 hours for columns. This was the fire protection specification. The thickness was based on a restrained condition, which meant that for a column, for a beam, and remember the size of those beams and the size in the standard fire test, those beams will actually, when they start to expand, they will be restrained at their ends. That's how they specified the fire protection, which meant there was ½ an inch of fire protection on the beams of those girders. If you look at the code in America, in section X3 E119, we note the following comment. In order to develop restraint, connections must adequately transfer thermal thrust to such supports. So that girder, oh, I thought I lost everything there, I started panicking. So that girder there, look at the size of it as well, 13.7, needs to have thermal restraint at the ends, okay? And that's got ½ an inch in it. The architect specified the protection. Structural engineer was nowhere near it. I'm glad someone laughed. So the architect specified the protection, not the structural engineer. No disrespect to architects. Any architects? No disrespect to architects. But you're not engineers. So there it is. There's a specification. Minimum beam size, concrete, lightweight, normal weights. Minimum thickness, ½ an inch. Unrestrained beam rating was 1 hour. Restrained beam rating up to 2 hours. Required 2 hours, which meant it was restrained. Okay? And as I say, typically in a fire test in America, you've got 3.7 and 4.8 metres. Remember the size of that girder. Right? So it's based on standard fire test, achieving 2 hours, assuming that it was restrained. Bit difficult to see, I know. This is technical drawing of that large girder and the connections at the end. And I'll just take you through it because I know you're difficult to see at the back. So the girder, this is that column 79. The column 44 was that edge column. You can see the columns. This is the girder. The way it was connected was it sat on a seating cleat, which is just an angle, like that, and the girder sat on top. And then there was a cleat to locate it on the top of the actual girder. So there was an angle here, and then there was a small cleat here. There was 2 bolts at the bottom, 7/8 of an inch, and 2 bolts at the top. If you take the gap at each end and add those together, you've got 88 millimetres. So you've got a beam or big girder that's sitting on some angles with 2 bolts at the bottom, 2 bolts at the top, with an 88 millimetre gap. Restrained or unrestrained? Unrestrained. Those bolts are just going to pin straight away. This beam is unrestrained, it's not restrained. So that beam is going to expand. It's unrestrained. And therefore, if you wanted that to be restrained, you should have put some shims down it to close that gap, following the code that said that there should be adequate thrust at the end. So, what's happening is that girder starts to heat up. You've got 4 bolts either end. Each bolt is a 7/8 of an inch. As soon as it starts to heat up, it's going to pin those bolts. And then that girder is just skating around on those angles. Going back to the protection. It was a sprayed protection. There was a number of ways that you can protect a steel beam. You can use things like brickwork or block work. Typical one that was used at that time was a spray. And when you spray these things, you spray everything else around it. The joke was usually, you should see some of the buildings in London where they sprayed with fire protection and you spray half of London as well. But you can see, the difficulty of this person holding this and spraying on this fire protection. So this was a sprayed fire protection, typically used. Nowadays we go typically for intermittence, but we still use spray protection. What I draw your attention to is that this is an underside of a floor, which is a trapezoidal floor. Fire protection is going on the steel beam. In some cases it goes on the steel underside. In North America it always went on the underside, so they put spray protection on the underside of the floor as well. But between the beam and the trapezoidal deck goes like that. The beam goes across, there's a hole, that's filled in with spray protection. You'll see why in a minute, but that's solidly filled in. So there you can see typically spray protection being put in on the steel beams. That's a picture of World Trade Center 7. Look at it very closely. Look how neat the fire protection is here. Remember, this is supposed to be 1/2 inch. Cool, they were keeping it at 1/2 inch. But look here, these are not filled in. So go back to the previous photo, you fill these in. Here, they're not filled in. Why is it important? Done a lot of research on this. The Steel Construction Institute did a lot of tests where they looked at cases where these voids were not filled in. The reason why they were doing it is actually if you had a board protection, filling in these voids afterwards is a real pain and takes a long time. So they were seeing, well, actually, if you had a beam typically set up like this but didn't fill in these voids, what difference would it make? Here's the difference. Test 1, top flange filled with the voids. You can see the temperature increase of the steel beam with time. Stand fire testing into it. And when the voids were unfilled, you can see that the beam heats up a lot quicker. So it makes a significant difference. So, what we've got now is that it was specified for 2 hours based on prescriptive-based approach. Actually, that was assuming that it was restrained. I think I've just shown it's unrestrained, which actually means if it only got 1/2 inch of fire protection on, means it would only survive 1 hour in a standard fire test. And then they haven't filled the voids. So actually it would only survive 40 minutes in a standard fire test. You're starting to get into very dangerous ground now on a standard office fire of this beam failure. And that's what happened. And you can look at this, and you can look at the fire. People will come back and say, well, it was 7 hours. Yes, it was 7 hours. But that fire was a travelling fire. That fire was travelling through the building looking for the weak point. That weak point could have been in the first 10 minutes, it could have been 7 hours, it could have been 12 hours. The fire kept on going until it found a weak point, and then it came down. Initiating event, it came down on that column 79, hit all those transverse structures, so you had horizontal progressive collapse, and then you saw the outside of the building fall. And if you look at the fire, which we've followed, all the photos we've got over those 7 hours, you will see a number of cases where the fire is raging in this area, or actually the fire is just passed and you're in the cooling stage of the fire. And no matter whether you look at a cooling stage or a heating stage of the fire, one is where the beam actually fails depending on the temperature of the office fire, or on the cooling stage where it's cooled off. Remember that girder was just skating around on those angles. So, very quickly then, if you look on the fire resistance, I'll quickly go through this because you might not be able to see it at the back. On a building this size, on the New York Code, they actually said you needed 1.5 hour fire resistance. Actually, someone decided in the design office, we'll increase that to 2 hours. That's great. So they increased it to 2 hours. So there was a design decision to increase to a Type 1B building, which was 2 hours. They then specified wrongly that the building was restrained, and that girder was restrained. So that design error dropped it to a 1 hour fire resistance. They then didn't fill in the voids, which was a construction error, which meant that this fell then to about 40 minutes fire resistance. And there you're in dangerous ground for a standard office fire coming to cause collapse. And that's what's happened. You can see the fire snaking around the building, trying to find a weak point, found a weak point, initiates an event, no redundancy in the system, no design against progressive collapse, the building came down. Some of you would have seen the NIST report, which is the National Institute of Standards and Technology in the US, equivalent to the Building Research Establishment in the UK. They carried out a lot of work and trying to understand what happened as a report. They made 1 or 2 mistakes without going into the detail. On the girder, they didn't get the latest drawings, which has what we class as shear studs in it. That was unfortunate. Reason why they made the mistake is because there was no as-built drawings. So things were changed during the construction time, and you literally found a handwritten note on a drawing where they've increased what we class as shear studs, and I can see the engineers in there because you're all nodding. From that report, which was in 2008, this is the recommendation 9. And remember, I've taken you through fire engineering. NIST recommends the development of 1. Performance-based standards and code provisions as an alternative to current prescriptive design methods to enable the design and retrofit of structures to resist real fire conditions, including their ability to achieve the performance objective of burnout during the cooling stage without structural or local collapse. So there they've said the prescriptive-based approaches do not work. Aim for performance-based approaches. And the tools, guidelines and methods necessary to evaluate the fire protection of the structure as a whole system. Great. So they're actually forcing the profession down to look at real fires, real behaviour. And that's their recommendation. What they should have done then is to look across the pond and look to see what we've done in Europe, which is actually, you did all that. Because if you look at the Eurocodes, they actually give the design methods for the performance-based approach. And what makes me frustrated, I think, with the States is that they could have used this as a foundation and built upon it. But no, they started from scratch, which was a shame because, as David knows, a lot of work has gone into this over Europe and developing these codes. That, I hope you enjoyed, was a quick run through, first of all, on what progressive collapse is all about. I gave you, and I'm sorry if I went into too much detail, about fire engineering and fire resistance. but then hopefully you can see what happened in the World Trade Center and why this building has collapsed, which is basically it was not designed correctly and there were construction faults which caused the building to collapse. Thank you. So one thing that's great about Queen Mary is that actually we're really generous. You wouldn't have got this at Manchester, I tell you, where I was before. And we've got a glass of wine for everyone downstairs, just have a glass of wine, have a chat. But before that, I am happy to take questions and answers. Can I say, I know there are a few people in the audience and are handing these out. Can I say, can I have a question though, not a statement? If you want to make a statement, you know, perhaps that's not too appropriate, but a question I'm happy to take, and I know there's quite a few. Okay, who wants to go first? Have we got some? Okay, I will work. So you go first. I'm trying to see whether there's. Everyone's sitting there for questions in the light page. You okay?
Thank you, yes. My question relates to a number of other reports which exist, and while anyone listening here would find it difficult to argue with your methodology and thoroughness of explanation, you make no mention of various aspects, including lakes of molten steel found maybe 20 stories below the collapse material, maybe 2 months after the event. And a number of other matters, lateral ejection of multi-ton steel frame members, distances of 600 feet at more than 60 miles an hour from the building. Now, could you answer me on, or give us an answer on why you haven't made any reference to this molten lake of steel, when the temperatures you've cited clearly do not reach anything like the temperature necessary to melt steel?
No, I mean, you've got to look at actually what happened with the evidence, and you can see all the pictures there that I've shown you, the issue about the molten steel. You've got to then start to think about, okay, if this thing has collapsed, and there's something still burning there, it's sort of covered by a lot of structure afterwards, and you know there could be something that's happening there at that time. But this was an explanation of the design faults of the building, and then how it actually collapsed. I am aware of all the conspiracy theories alongside that. All I can do as a structural engineer is look at the evidence that's in front of me, and as I said, you can see how many years we spent on this, and looking at all those evidence, I've given an explanation based on structural theory and based on fire engineering as well.
I've already alluded to that, and you haven't answered my question.
Okay, thank you. Okay, I'm going to take a couple more. Oh, I'll take one here. That's okay.
I'm not an engineer and I'm not an architect.
That's good. That means I haven't upset.
I would say I'm not an engineer and I'm not an architect, so layman, so it was very interesting for me. 2 questions, if I may. Firstly, what were the lessons learned from the effects of the firebombing in the Second World War?
Sorry, I didn't get that.
What lessons were learned from the firebombing in the Second World War on the structure of buildings as they were then? And you said that the Europeans had got together and formed standards, and it was regrettable that the Americans hadn't worked to develop that rather than starting from scratch. Could you say a word about European collaboration and how this might progress in the future, given current developments?
Cool, I'll tell you, I'll just line myself up. Let's take the first one first. Yeah, I mean, there were experiences, and when you look at legislation, all legislation has been built up on disasters, what's happened learning from those and tweaking the building regulations. Sometimes you need to step back from those and think, well, actually, are we going down the right route? And you can see that after the Bradford fire, the Walls fire, but also, of course, what happened in the Second World War as well. Coming back to Europe and Brexit, in the UK, we did, we've got fire performance codes in steel codes. We had 5950 Part 8, and when I was at BRE, I was chairing the working group to develop that and revise that. But working in Europe, the British codes then were superseded by the European codes, and us working through some looking at developing those codes, and a lot of experts from the UK really drove those European codes forward. Going forward with Brexit, that's the challenge that we've got right across the board. But there's no way at this stage we can go straight back to British codes. We're going to have to carry on with those European codes, and there's discussions, I know, on that as we go forward. But this is just one part of codes practice that we need to address. Okay, I'll take a couple more. Go on, and I'll take one down here, and then I'll take one at the back. And then, can we call it a day? I'll go downstairs, but I'll need a drink.
Hi, here we're saying I'm a proud graduate of Queen Mary University of London, and I'd like to congratulate you on your inaugural lecture.
Thank you.
So yeah, there's
it's a brilliant university.
yes, definitely. Just going forward, so moving back from the performance-based and the prescriptive-based design approach, what are the differences in safety factor, and what are the financial implications on, you know, how much more money does it cost to go for that, for the performance-based over the prescriptive base?
Yep, okay. Great question. Let's take the money first of all. On the design costs, enormous. Let's be honest. So if you had a steel frame building or a concrete frame building, prescriptive approach, I can design it in half a page. Right? Job done. Followed. Approved document B. Fine. Performance-based approach, depending on how much detail I go into on the type of fire, the thermal response and the structural response can be this thick.
Surely there's a difference in insurance costs as well?
I'll come back to that in a minute. So I'm doing the design costs first of all, and that's the major thing, because clients are saying, well, what am I paying for here? Because I can just follow a prescriptive-based approach. Why am I going down the performance-based approach? Remembering, for legislation, all I need to do is get over the minimum for life safety. So there's a cost there. Comes to the cost of construction, well, that depends. So let's take the shard, for example. Now the shard, when you look at the steel structure of that, what we class as secondary beams are not protected, because we've used the cantilever action of the slab to carry the loads over those unprotected beams onto protected beams, which are our main beams going between columns. So in that case, there's a saving, because we're putting the protection where it was required based on the performance of the structure on a real fire. But then when you go to the columns, the prescriptive approach told us that you only need 2 hours fire protection. The performance approach told us you needed 3 hours fire protection. So actually we put more protection on the columns and no protection on the secondary beams and protection on the primary beams. So what does that mean as a performance-based approach? You're not always saving money. You're actually putting the fire resistance where it's required, not all over the structure.
So you've failed to review process of the Hulsey study, have you? Because you failed to mention it. I can't believe we've been here for an hour and a half and you've not mentioned the University of Alaska Fairbanks study by Professor Hulsey. Have you fed into the peer review process? Because you've obviously put a lot of effort into this.
Can I just answer this question?
Well, I think you ought to answer that question as well. You've completely ignored that.
No, I haven't.
It is very important.
I haven't.
It needs to be addressed.
Major point.
Because academia has failed on studying 9/11 over the last 17 years. And the war on terror is hinged upon all of this. And this is the weak point of the entire narrative. And you are just restating the official narrative. So have you fed into the peer review process of the Hulsey study?
I will give you the next question, right? And I'll let you speak again. Can I just reply to this question and then I'll come back? Okay, out of fairness, he asked the question.
Well, I think you've got a lot of pre-scripted questions from your students here.
Oh, no way!
Right,
What?
Enough. I'm sorry you think that.
Well, it appears to be the case.
Right.
Why haven't you mentioned the University of Alaska Fairbanks study in that case?
He's going to in a minute.
You should have mentioned it an hour ago.
Right.
3,000 architects and engineers.
You haven't mentioned
That's
them
fine.
either.
If you want to make a
Oh,
statement,
shut
I'm going to
up.
call this to an end.
I will not
Okay?
shut up.
If you're going to make a statement, I'm going to call this to an end. Right. I apologise to you. Okay? I've been here 6 months. I do not know the graduates here. Okay? And I apologise to you. To answer your question, first of all, I've answered the question on the cost of the design. I've answered the question on the cost of the structure. The issue about robustness and insurance costs is another issue. The insurance costs, the insurers look to see what is the cost of replacing it. So some people say if you put more protection on it, i.e. protect it for 4 hours, surely the insurance cost will be less. Any fire will cause damage and will cause damage to a structure. And you might get damage to the structure which is minimal damage, but you still got to cut that structure out and put the fire protection back on, which is a cost. And the insurance companies look at that. If you've got no fire protection on your secondary beams and you still cut that bit out, it's a lot cheaper. Okay, so that's the insurance cost. Right, madam, let me come to your question. Do you want to make a statement first and then I answer?
I've made my statement. I want to know whether you fed into the peer review process.
Right.
You failed to mention Barry Jennings, who was the janitor who was stuck in the World Trade Center 7 for several hours and was talking about explosives and was interviewed. You failed to mention the 300-odd firefighters who have an oral history project online, which the New York Times has, where they talk about explosions in the basements of all the buildings. You failed to mention Bobby McIlvaine. You failed to mention the fact that NIST never tested for explosives in their report. You haven't mentioned the fact that the 9/11 Commission report didn't even mention World Trade Center 7 in it. And you haven't mentioned the Hulsey study or the architects and engineers. I think most people here might realise that Building 7 is the Achilles heel of the entire 9/11 narrative. And on this event rests the entire war on terror. This is the justification for the invasion of all these countries that we have seen over the last 17 years. And I spent seven years in Afghanistan and 3 years in New York. I have just come back from New York, where I have met people, I have met firefighters, I've attended these events, I've been to these conferences, and I must say, you are restating the official narrative while ignoring the work that has been done by AE911truth.org. And I think that you owe them an explanation for that.
Okay, thank you for that. Interesting you talk about consequences and the war afterwards, because that's also what, when I was at Manchester, I taught our students as well about consequences of failure. If those towers hadn't collapsed, what would have happened afterwards? It's an interesting political question, which engineers need to think about as well.
That's why
And
academia
let me
needs to address
finish.
it.
Let me finish. Okay, I've given you time. Let me finish. Otherwise, I will call it to an end, and I won't carry on.
Well, don't call us conspiracy theorists then.
That's true.
We're analysts.
Okay. If I've upset you in any way during the talk, I was trying to be balanced. If I've upset you in any way, then I do apologise for that. Okay? I've tried to give an explanation. I've also teach my students, I don't teach anymore because I run the university, but in my previous university, I teach my students all about risk. And the risk, of course, is the probability and the consequences. Okay, if you don't want me to answer or carry on, then we'll call it an end. Okay, thank you very much. I did try and answer the next bit.
I came here tonight because I was interested to see what Professor Bailey had to say. It wasn't very clear from the title of his lecture whether he was going to be restating the official narrative or actually contesting it. What I found very surprising was that he spent an hour and a half, we had an hour and a half in the lecture theatre, and he didn't once mention the Hulsey report, the University of Alaska Fairbanks study into World Trade Center 7, which has already made its interim conclusions that fire did not cause the collapse of that building, and I believe is due to conclude fairly soon that actually explosives were involved. Neither did he mention the oral testimony of the firefighters in New York who talk about the numerous explosions and bombs going off and so on, and I've met some of them while I was living for 3 years in New York recently. Neither did he mention the fact that the NIST study, which was it was a political appointment by the Bush administration, the head of NIST, and that they withheld their data and have not allowed it to be analysed by other scientists. There's been a pitiful lack of interest in 9/11 in academia generally, and those who have dared to look at it have been summarily dismissed from their positions, such as Stephen Jones. Others haven't been able to publish papers, or where they have published papers, such as Niels Harrit, publishing on the presence of explosive devices in the nanothermite in the World Trade Center dust. Their papers have gone unanswered. I find it extraordinary that in his hour's lecture tonight, Professor Bailey mentioned none of those things and focused on some very narrow interpretations which reinforced his underpinning of the official narrative. The question is why he's chosen to give this lecture at this point, and I believe it's a limited hangout prior to the release of the Hulsey study, so that anyone who is analysing this more closely can be castigated as a conspiracy theorist and essentially sidelined and marginalised.
It is an inaugural lecture that he's done, so it's presumably the first one here, and we've got possibly a new brush sweeping clean in some ways. And it would be quite a topic that would be guaranteed to get quite a large audience, wouldn't it?
Of course, but let's challenge Queen Mary College to hold a 2-day seminar with architects and engineers from New York, with Richard Gage, with Barbara Honegger, with some of the Tony Zambotti, some of the architects and engineers from the United States, from New York. Let's bring them over here and have a proper debate. Isn't that what academia is supposed to be about?